So,
Ask you this in your scripts on size. Do you know how to do that? Can you one more time, please?
so this is the goal for today's class. I will try to finish our script. Then I will try to discuss the answers of the quiz, and I want to clarify some things what I think I didn't mention last class. And if you guys have any question, because last class, after class, Aman asked me several questions. I think everyone maybe have some questions, so feel free to ask your question. So last class, after calling all the library, I showed you the raw raster file, which I got from after the processing of all the images, stitching and everything. I got that raster file and I showed you here. You guys don't have this file because that is really big and it takes several minutes to load in R. Then I showed you the file which is segmented. I mean, I removed all the soil pixels from my raster file. And then this is the point where we all started our coding. This is a resampled segmented hyperspectral image. I coarsen my data really big into big chunk, big pixel. After that, we saw some of the header, some of the bands from our raster file. And then we called our plot boundary. So here one thing, we could have just called our plots, but instead of that, I called only the points from where I collected my samples, and then we tried to make a buffer. In that point, I want to change one thing. At last time, we all made a buffer of 5 meter, but later I thought that my pixel size is 5 meter, and if I make a buffer of 5 meter, then it will be just the same pixel. That's why if we can change the distance of that buffer into 15, it will be good. And then we did the map view of that buffer. Then we changed the SF object into vect object because we are working with Terra package. In Terra package, for raster, we use Rust, and for vector, we use vect function. If we already are in the same position right now, then this is the key part of our exercise, that here we are extracting our values from the image. We call the name, I try to call the name as average spectra because I'm extracting my values depending on the mean, depending on the average of the pixels. So if my plot has 20 pixels, then it will calculate all the pixel values and I will have the mean value. Here, different literatures done the same thing. I mean, extraction of the values, reflectance values in several ways. But I am doing in this way. So in hyperspectral is under kind of exploring and developing workflow. So there is no thumb rule, or there is no thumb rule that you have to do in that way. I am doing in this way. So I am calculating the average of the pixels for each plot. Okay, for that, I will try to call the function extract because it will extract my values. So if we just type extract and don't hit enter, for my in my script, it is showing that extract is coming from tidyr library. If it is for all, then I will not do in this way. I will try to do because I want extract from Terra package. So now it is coming from Terra package. And if we do a little help or little search here, the extract works like it asks me from which raster file it is taking its data, then the vector or the field shape, and the function. So I believe my TIFF file name is HSI. It is not. Okay. Just give me a moment here because I want to make sure my vector file is, my raster file is okay. Okay. Raster is sample. Okay. HSI is sample. Okay, HSI. It is doing. Okay, this is my raster file. Then I have to give my plot boundary, which is plots buffer v, and then the function, I want it as a mean. And of course, as there are lots of NA values, because I removed all the soil pixels, I have to call na.rm equal to true. Now, if I run it, I hope it will run. Yes, something happened. So why it is not showing ages? Yeah, so I put something wrong. HIS resampled for me. Okay. If everything's right and everyone are okay, then we can move forward. So this is the key part of this exercise. Now I have all the bands and with all the reflectance value for each of the plot. I have 21 plot, and against 21 plot, I have 272 band reflectance value. Now, if I have my table, I can do my analysis in different way. But now we had our goal yesterday that.
Hey, Niva, can you scroll a little bit on the chunk above?
Yes, sure. So we extracted values from our TIFF file, which was HIS resampled, I believe. And then the field boundary, which is plots buffer v and mean. Okay.
Then you use this for the number of why we have the number of now we have 270 columns.
Yeah, so here we in our data frame we have 21 into 273 because we have 21 plots. So we have 21 rows, and against each rows, against each plot, we have 272 bands. That is why we have 273, and one is for ID, or 272 bands. If we go, we can see each and every band are here. All right. Then we can move on. So our goal is to make NDVI, to calculate NDVI. That is the main part where multispectral differs from hyperspectral. So if we see in multispectral, we can make just one NDVI because we have one red band, which has a very high bandwidth, and one. Yes, Tifton.
We are having an issue. The chunk is not working for us.
All right. So have you tried to call extract from Terra package?
Yes.
Still?
All
right. Yeah. So can you please check the name of your raster file, because it gave me error because I didn't spell it right.
I checked because I copied and pasted, but still doesn't work.
What is the error are you getting?
Saying error in H, simple error method called error in evaluating the argument X in selecting a method for function extract. Object HIS resembled not found.
Okay. Which object?
HIS.
Okay. So have you? That means you didn't run, or it doesn't find the raster file. So make sure that you run your raster file, which was here, resampled, whatever HIS or HSI resampled. Make sure you run it. It should work. Then check the spelling, because it should pop up. When I write, it should pop up. It wasn't popping up for me. That's why I was confused. So it should pop up here. Is that okay, Polly? Or Benny?
Trying to fix it. It's not working yet. I'm trying to fix it.
So have you noticed how I wrote the mean? I put quotation mark around mean.
Yes.
Yeah, I think it's on the creating the object is probably
the
issue, because the error is saying object not found.
Yeah, object not found. Yeah, it should. The error should be relating with the raster file or TIFF file. Can I? Okay. So they are working in there, so I can't ask for the script, right? You can see. And if other people, do you have any issue, or you can just you can run your script fine? I mean, is that fine for Marco, Luke, then Kathy?
I just checked, and the spelling is the same as yours. But in my case, I have an error that says error in extract
All right,
function.
so there one thing, spelling shouldn't be same as me, because it may be different from yours and mine. I don't know. You just copied the name you used here.
Yes.
Then it ran.
They didn't know this, were they able to create this object?
Yes. So your raster file worked, right? You can see the raster file.
Yes, I can see the raster file.
Okay, then copy this name.
Mhm.
Copy this name and use the same name here, because the raster file should be same.
Yes.
Okay. So when you are writing the name of the raster file, it is popping up. That means you are using the same name.
Yeah.
Then it should work.
Yeah, it's working for me.
Yeah, if the name are same, it should work.
Yeah.
Aman is fine. Yeah. Kyathi is fine.
Yeah, I'm fine. Thank you.
Then now, who has the problem right now? Marco or so the problem is related to the raster file. If you put the name correctly, it should work.
Okay.
Is that working, Marco?
Is that working?
Not yet, but I will look into it. It's okay.
But it should work because it's not that hard. Just the name. The name should be same, then it should work. And have you tried the extract from Terra package?
Yeah.
You can tell Marco that if he still have issues, ask him to open an issue on GitHub and I can help him.
Okay. If you have any issue still, you can put screenshot and make an issue in GitHub. I think Dr. Bastos can help you.
Yes, sure.
I think if you just give screenshot of the raster file, the plot file, I mean plot name, raster name, and this extract chunk, these 3 chunks would be good enough to solve the issue.
Okay.
Because it's just name. All right, moving on. Sorry that it didn't work. Okay. So what I was saying that in multispectral, we have 2 bands, one band for red, one band for NIR. And if we want to calculate NDVI, we all know that NDVI formula takes only 2 band, NIR and red. Multispectral will give only 1 NDVI. But in case of hyperspectral, we have several bands under red band, because one red band is divided into several bands. Similar, in NIR band, multispectral gives several NIR bands. If we look into here, that for our sensor, it gives band number 105 to band 132. It means our sensor gives 27 bands, 27 red bands. And for NIR, similarly, it gives 137 bands, because NIR band is range, electromagnetic range from 700 to 1000 nanometer. And under this range, our sensor gives band 137 to it should be 272 bands, which is 137 bands. Did we understand this? Or anyone has any question here?
I have a question.
Yes.
So, saying 27 bands, do you mean red band, like others 27 red bands, or there are different bands?
No, 27, all 27 bands is red. All 27 bands described as red band. So 105, band 105 is red band because it falls under the zone where red band works. Similarly, 106 also red band, 107 also red band. All the bands falls under the range of red band. That is why all bands are red. So this is the main difference of hyperspectral and multispectral. Hyperspectral has so many bands under same electromagnetic range. That is why it gives us different combinations of vegetation indices. So we are talking about just NDVI. Let's say if we want to calculate NDRE, red edge NDVI, green NDVI, there will be several numbers of combinations of bands. As we are discussing about NDVI, and we have 27 red bands, 137 NIR band, we can calculate 3,699, almost 4,000 combinations of NDVIs. 4,000 NDVI. That is the superiority or beauty of hyperspectral. Does anyone have any question here? Yes, someone.
So by that we mean that there are like 273 rows in our data. So we are talking about like we have 27 red bands out of 273 and 157 NIR bands out of 273.
Yeah, so Aman's question is, we have 27 bands out of 272 bands. It means we have 27 column.
Yeah.
27 column of red bands and 137 column of NIR band.
Okay.
If we go upward here, we can see that, let's say this is these bands are coming from blue region. So 41, 42, band 43, all are coming from blue band. And similarly, if we go further, okay. Oh, it will take so much time if I want to show you the red band. So I hope you all understand. Yes, Dr.
Use renewable volume from the
Yes,
side.
yeah.
Awesome. Hi, everyone. I just wanted to perhaps just perhaps clarify a little bit. So if you imagine, as we already talked about, I think you saw this map here, both on Eva's lecture last class, but also when we talked about the remote sensing class, that I showed you the electromagnetic spectrum with nanometer on the x-axis and reflectance on the y-axis. If you remember, generally, we refer to the red band from being from the 600 to 700 nanometers. That whole chunk of the spectrum we call red, right? For our multispectral sensors that we've been using both with drone and satellites, within that entire, so from 600 to 700 nanometers, what we call red, we had one band in that space. Now, with hyperspectral data, you have 27, right? So as Neva was explaining on the first lecture, is it a 2 nanometer resolution, Neva? So so imagine that from 600 to 602, that is the first red band. From 602 to 604 is the second red band, all the way to 700. That's why you have set 27 red bands. They're all cutting a different sliver of the entire part of the spectrum that we call red, which is 600 to 700 nanometers. So that's why we have 27 bands on the red spectrum with hyperspectral and 137 on the near infrared part of it. So that's what Neva is making the point here, is that with multispectral, we get one red, one infrared. Now we have 27, is that right? 27 red bands and 137 near infrared bands. So imagine that we can do all combinations between each red and each near infrared, and each one of those combinations will give you a different NDVI value, right? Because it's using different bands, both from the red and the near infrared. So I guess I just wanted to clarify that. And if anyone has questions on understanding that concept, please let us know, because now we're going to get into an exercise where you're going to calculate all those potential almost 4,000 NDVI indices, where each one has a different red and infrared band information. Any questions about that?
Thank you for the clarification. So does it mean you can base on one, for example, if you have 27 red bands, and let's talk about the green band. If we have maybe 30 green bands, can you base on one green band with another combination from the near infrared, maybe to say like this is the how can I say, this is the correct band to base on when doing any analysis for the plant here.
Wally, that is exactly what Niva's going to show you. So towards the end of this exercise, you're going to realize that there is a very specific combination of one specific red and one specific near infrared that when used on an NDVI formula gives you the best correlation with what Niva is studying, which is aflatoxin in the field. So that's
Okay.
what we're going to show. Yeah.
Yeah, thank you.
All right, thanks. I guess before I turn it over to Niva again, any questions that I can help with? All right, Niva, turning over to you. So I'm going to mute.
Thank you, Dr. Bastos, for clarifying things. And I encourage your questions because I know this is something different from other sensors, so feel free to ask. Yes, that was a valid question for Polly. How do we know which band, which red band or which near infrared band we are going to use? So our goal of this exercise is to find out that. Before going there, I want to mention one thing, that how do you know which band falls under red zone, which bands are falling under near infrared or green zone? So it is specific to sensor. My sensor starts from 398 nanometer, and it ends in 1002.74 nanometer. So this is the whole range under which my sensor works. And sensor gives us the nanometer the information which band falls under which nanometer. And from that information, we start our analysis. All right. Then moving into calculations of all NDVI combinations. So this was our band information, which coming from average spectra. We are going to use that. So this is our data average spectra. Now we want to select only the specific bands, red bands and near infrared bands. Let's start coding here. So here I want to select the bands, and the bands are in columns. So we are going to use select, not filter. So let's start coding select from dplyr, and I am selecting band. What is the number of red band? Red band starts from band 137. Band 137 to band, oh sorry, not 137. Band starts from 105. 105 to band 132. Okay, this is coming from red band. Then we are going to select the NIR band, which is from band 137 to band 272, which is the very last band of this sensor. Let's run this portion and check what is the NDVI all is giving us. So here the bands starts from 105 and it goes all the way to 272. Now I want to add the ID because it doesn't look good. So let's add the ID column here. Okay. ID column and all the red bands and all the near infrared bands. Okay. All right. Then I want to pivot. Okay. Let's one more time. Let's check what we got here. All right. So now that I have the ID column and all the bands, and my goal is to calculate NDVI, what I need here. To calculate NDVI, I need one column with all red values, red reflectance, and another column coming from near infrared reflectance. Then I can calculate, then I can calculate the NDVI. To do that, my plan here is to do the pivot. So first, try to do the pivot of the red bands. So it will be easy for us to do the NIR bands. I left the code here. So for pivoting all the bands coming from red range, we call the columns coming from band 105 to 132, all the bands. And then I will put the names into red band column and I will put the values into red value column. Let's run this chunk of code. Okay, I forgot my pipe here. Let's put a hash here, then try to run this part of the code. Okay, I guess it. No, it should give. Our table is different here, so it should give. All right, let's do another thing. Let's do the pivoting of red band, NIR band, then I will check. Then we will check again. To pivot the NIR band, let's do like this, pivot longer. Then the column names, calls equal, the bands are coming from band 137 to band 272. Names to NIR band, values to NIR value. Yes. That's it. Just give me one moment here. Okay, maybe it worked last time, but somehow I don't figure it out. Okay. If you all, I'm giving you just some minute to catch up the codes. It's similar what we did in red bands, the similar thing we did in NIR band. just change the column range and the name. Instead of red, we are using NIR. And this is our output. Under red band column, all the bands are there. And the red and the values, that which means the reflectance values. NIR band, all the bands are there, then the values. So this is for one red band, and all the NIR bands are there. All 105, then I believe under 1. Okay. So this is the combination. That's why all the red bands are there. Then the near infrared bands changing. After certain point, the red band will change. Yes, the red band will change, and the combination of NIR band. So if we see the number of columns here, that we have 5 columns and so much more rows. This is because of the combinations of red and near infrared bands. Okay, if we all are here, then we try to calculate the NDVIs. This is the formula. I know all of us is familiar with this formula. Then we want to create the NDVI column. As we are calculating NDVI, we want on column which name will be NDVI. To do that, we want to mute it. And the name I want to give NDVI band. And what we are expecting here under this NDVI band. So under NDVI band, we will have the names with the combination. So when we calculate NDVI, it takes values from 2 columns, one from red band and one from NIR band. So the name will be like band 105, which is coming from red, / another band which is coming from near infrared. We want to give the name like this. That's why I am calling the function here paste 0. The name is coming from red band. Underscore name coming from NIR band. If we run this chunk, after pivot longer, I missed this. Thank you, Aman. Okay. Oh, I missed to mention one thing. Sorry. So when we are calculating NDVI, this is our new column which gives us the value of NDVI. And now we just created the band name which will contain the names. So previously we had red band value, NIR band, NIR value, and then we calculated and we gave the formula and we calculated these NDVI values, and finally we just give the name of the NDVI band. Under this band, it is saying this NDVI value is coming from this red band and this NIR band. Does it make sense? Has anyone any issue? Does anyone have any issue here, or any understanding, or did you miss any coding part or anything? All right, if everyone is fine, then let's move on. I'm just giving the pipe here. So from this table, what we need for our further analysis, we are gonna need only the NDVI and the name of NDVI band. So in this part, we are removing all unnecessary columns, and we are keeping we can do it in two ways. Either we can remove all the bands, all the columns, or we just keep our selected columns. Let's select, and I want to keep ID column, NIR value column, sorry, NDVI column, and NDVI band column. Okay. So in this part, I am keeping only the columns I am interested in working. Let's check the data. We have only 3 columns here. If we all are in the same page, then we want to do a little pivot wider here. To do that, we will call the names, which is coming from NDVI band, and values coming from NDVI. After doing this little pivot, we'll get this. So this is the ID column, all the bands. The band, I guess we already understand how the name works. Red band, near infrared band, red band, near infrared band, and all the NDVI. So we calculated our NDVI combinations, and we have 3,800 columns. We calculated this much NDVI. Does anyone have any question here? All right. If no question, then we can move forward. As we have our NDVI, now I want to call the name of our target variable, because without target variable, we can't do further analysis. So our target variable is here aflatoxin, which is a toxin. As I mentioned last day, that we collected samples and we sent it to the laboratory, and they gave us the values that how much toxin is present in that sample. Okay, to do that, before going to the aflatoxin, before calling the name of the aflatoxin data set, we want to do little thing, which is in here we have our ID values, but we don't know which ID is coming from which plot. But our aflatoxin value has its plot numbers. To do that, we want to do little thing here. So we want to give the plot numbers here. To do that, what was our data set name? NDVI all. NDVI all. And in NDVI all, I want to give one more column, That is why I'm doing here muted. And I want to put the name of the column is plot. Plot. So I believe Dr. Bastos already did that in one of his exercise. So I believe you already know that, but still I'm doing it again. So to give the name of the plots, we first have to give the plot number from where the plot number starts. For this field, the number starts from 701. This is 701, and it gives till 21 number of plots. We know that there are 21 plots, but what if we don't know the number of plots, how many plots are there? But we know how many rows in the ID column, right? So we want to do like this. From 701, we will go how many row we have. N row in NDVI all. So starts from 700 going till 701 plus in number of row, but then it will be more column. Yeah, the row number will be increased by 1. So we are subtracting the number 1 here. And then if we just run this column, run this chunk, it will give, okay. So I don't see the newly created plot column here because it went to the very last column, but we have more than 3000 column, and it's really hard to go through all the way. That's why here I will select which column I need. Here I need all the columns, including the newly created plot column, but I want plot column the very beginning. So I'm still doing like this. I want plot, then everything. Okay, if we do like this, the plot column will be at the very beginning. All right, if we all did this, then next we want to move on to call in our target variable, which is aflatoxin. Is in a CSV file. So read CSV, and we want to go to our data folder, and the name of the CSV file is TEFT7 aflatoxin results 2023. If we run, then all the plots are there, and against all the plots, all the aflatoxins value are there. Okay, if we catch till this part, then now what we want to do some wrangling, because the name of the column doesn't seem good. After plot, there is 1 dot, and it doesn't make sense. Here we want to do some wrangling. So our data is coming from AFL. This is our AFL data. And we want to rename. We want to rename this plot column. I'm copying the name of this column. So to rename, I want the column name would be plot. Why? Because just 2 chunk above, I created 1 new column with the name of plot, where all the band NDVI combinations were there. And now in aflatoxin data, I want to change the plot column into plot. And also I want to change this column name into aflatoxin milligram kg, because aflatoxin has a unit which is milligram per kg, and giving the original name of the column. Now if we run aflatoxin clean chunk, this is the data. This is the table with plots and aflatoxin values. Here I want to mention one thing, that when we had our NDVI combinations or reflectance values, we had 21 plot, which is here 21, but our aflatoxin values are not coming from 21 plots because of some limitations. We only have data from 17 plots. So now we will be working with 17 plots only. So now I want to just merge both of the data set. To merge, we already used this function several times, left join. So to do the join, as I mentioned, I have lesser number of rows in aflatoxin clean data. That's why I put it in the beginning. Then I used left join, and I'm joining the NDVIs because it has all the combinations of NDVI values. And after that, I want to make sure that my data table would give me first the plot column, then the aflatoxin value column, and then all the NDVI band combinations column. If we run this chunk, I already put everything in that chunk, so our final data set will be like this. Now, for further analysis, if we want to save this data set, we can do one write CSV, so that we have one CSV file with this data, with these combinations, rows, and everything. But this is just an example, that's why I'm not doing that, but I'm just putting the code here if in case. All right. At this point, I want to make sure if everyone are on the same page with understanding and with coding, or anyone has any issues or questions. Oh no? All right. Aman says she doesn't have any question. I believe everyone is fine. Then the final stage of our exercise. So one of the goal of this exercise to get the best combination. So here is one combination with band 105 and 137. There is another combination, and there are so many combinations of NDVI. But which combination is best? Which combination is best to explain our aflatoxin values? Which predict the most efficient way. To do that, we are going to do little modeling here. We are trying to do one linear regression. So to do that, when we do any regression or any correlation, we can't use the table like this with all the bands name in column format. So we need one column with the names and one column with the values. So we are doing this here. To do that, we want one pivot longer So we put the name like this, aflatoxin NDVI long. We want to do the pivot longer. Before doing the pivot longer, our data is coming from where? Our data is coming from the previous chunk, aflatoxin NDVI. Always I try to copy so that I don't mess up with the name. Although the name pops up, still I call the name, call the data set name. Then I want to do the pivot longer. Let's check how the data looks like. The data looks like this. So I want to use these columns. So calls equal, the call starts with band. So as all the columns are same, it is easy for me to give the structure. So this is like this band. Then my new names will go to band column. We did this pivot longer previously. If you can recall, we had one column with NDVI band and NDVI. We are doing similar thing here. And values to NDVI. If we run this, we get the plot column, NDVI value column, band with the name of all the combinations and NDVI values. So we did little coding here. So I'm giving some time to catch up. Okay, if everyone's fine, then we can move on. So now we want to do a little regression where this is the aflatoxin column is our target variable and this NDVI value is our explanatory variable. So we want to get the best NDVI combination to predict our aflatoxin value. We can do it when we do regression. There are so many metrics, but we want to stay with just R-square value because we all know the model which gives the maximum R-square is the best model. Now we are trying to run a regression. Here I left all the codes because we didn't do any regression in this class. That's why I didn't want to break this. But here we want to understand what the code says. This is the name of, this is the name where I want to put my regression values in NDVI reg, and my data is coming from aflatoxin NDVI long. Now I want to do a group by. The group by will be according to band. So all the bands will react like one variable. For that, I did a nest. So after this is one part where I just put all the variables in one place. So all the bands are one row. All the bands, because one band has several plots, right? One band has 701, 702, 21 band, 21 plots, 21 rows. But I want all the bands as one row. Then this is the regression part. LM aflatoxin milligram kg by NDVI. So this is the main part where we let the R know that this is the thing I need, I want one linear regression where my target variable will be aflatoxin in milligram kg, and this is my explanatory variable. So explain, or let's see how the NDVI will explain, or NDVI can predict my aflatoxin. Okay. Then we want to see the summary. In summary, it gives other metrics like slope, R square, and in this kind of thing. But we only need R square value. That is why this part of code saying that I want only the R square value. And the R square value I want in a new column, which will be R2 or R square. In this column, I will have my R square value. If we run this chunk, or this part from this chunk, we'll get like this. So in table, all my nested data there. So this is my band. If we have one combination of 105 band number 105 and 137, it will give this R square. And with this combination, it will give me this R square. I just want to select my best model depending on the R square value. So this is the first red band, red band, and then first NIR, second NIR, third NIR. So my data set is structured in a way according to band number. But I want best R square. That is why here we did an arrange. So this column or the whole data set will be arranged in a way the maximum R square will be the first one. Now this is the best R square, which is 0.23. I know this is not the best, but here this is the best. And to get this R square, we have to use this combination. So the red band coming from 122 and the NIR band coming from 167. So now, Polly, do we know which band combinations we are using? Which band from red, which band from NIR we are going to use? Here is the answer.
Thank you.
All right. So this was the goal of this exercise. I want to ask if anyone has any questions here. No. All right, then we can move on. Okay, so I did that previously while I was working with this data, and it gave me different results. But today it gave me, it gave me different results than today. So previously I had 127 band, which was coming from red band, but now today it is giving me 122. So I want to update this number, and for NIR band it is 167. So for
I just want to mention that I believe that the difference we're getting here is because of the buffer.
Oh,
The
it
size
could
of the
be.
buffer is not very much.
Yeah,
So I think that's, if you want to mention that,
Yeah.
line, just so.
All right, so Dr. Bastos mentioned one thing. So previously I wanted to show the plots, only the plots of the field. That is why I got that band number. But today I only showed the buffer around the sampling points. That is why that could be the different, the band could be different. All right. Now, one thing, as I have some time here, one thing I want to see, which is the how the NDVI looks when I use band 122 from red and 167 from NIR, how the NDVI looks. Here, I want to mention one thing. These two bands giving me great combination, but it not necessary this band giving me the best NDVI values. I mean the highest NDVI values. It could be. All right. To get the NDVI plot, I am calling the name of my raster layer. I want to make sure if it is right. HIS. Yes. So HIS resampled because it popped up. To get the NDVI, to get the image, get the NDVI image from that raster image, we are doing this part. So I'm calling the raster layer, which is HIS resampled. Now, if you remember that while we were using the TIFF file or raster layer, we used rust function because I mentioned there are too many layers stacked together. That's why we used rust. But now I want to see just one layer, one NDVI layer. That is why I have to change this rust into stars. So let's do that. To do that, you already did that. ST as stars. Then I want to split the bands. That is why I want to use split. This is new. I never used this function. Dr. Bastos taught me. Thank you for this. So the split, how it works, it is splitting all the bands because I have 272 bands there all together in resampled layer. But now I want just two layers, one NIR layer and one red layer. That is why I am splitting the bands. Yes.
If you run HIF resample until STS stars, you just if you run until that point, and it brings
okay, let's check. Let's check how it looks when the
So what you see here is if you go on the first panel,
yes,
there's just
all
one column.
yes, one column, yeah.
But if you go on the second panel on the data frame, you see that there is a dimension X, Y, and a dimension band. So all the bins are kind of hidden away on that band dimension. So by doing the splits, we'll bring them into the first panel, which is then how we can use them like in tidyverse as far as calling them names.
Can you explain that? I
Sure.
want to.
Yeah. All right, so just wanted to give a quick example here. So if you just run that HIS resample pipe STS stars and look into that, which is what Neva is showing on the screen, can you scroll up a little bit, Neva, just to show them? Yeah. So right now, the way that the stars object is working is it has all those 272 bins, but they are kind of stored away. Can you go on the second panel there, please? Yeah, so right now you see this is the dimensions component of a star's object, you see there is an X dimension, a Y dimension, and a band dimension, right? This is that hypercube that Neva was referring to. This is a hypercube with 272 layers, right? Now, for us to be able to call those specific bands using their names, their column name, if you would imagine, we have to basically take all those 272 bands from that dimension, which is on the second panel of the star's object, and bring them into the first panel, which really shows you each one of the band names with a statistical summary. Once we do that, so then we can refer to each one of those band names just like we've been doing with other stars objects. So I guess just to quickly summarize that, right now, all those 272 bands are in a dimension of the star's object. We want to bring that as an attribute into the first panel. That's what the split band function is doing. So once, let's see, Niva, if you allow it to go through and on the split band line, and if you just add a pipe after the split band to block that pipe. Yes, and then now if you run that same object and you print it, okay, that's what you're showing. Yeah, perfect. You see now that on the second panel of that print, you do not have that band dimension anymore because now they've been brought as an attribute on the first first panel there. Yeah, so that's what that split band is doing. I guess any questions before I turn it over to Neva? All right.
Thank you, Dr. Bastos, for clarifying these things. This is also new for me. Good. So as Dr. Bastos mentioned, that split worked here so that we can have all the layers separately. The HIS resampled one layer is splitted into several layers. So all the layers are here. Okay. Now I want what I want. I don't want all the bands, right? I want just one specific red band and one specific NIR band. That's why I want to do a select, dplyr select. And what is the name? Okay, so I want to select the red band, which is 122. Yes. Band 122. But I want to give it a name. That is why I'm doing it. Giving the name is red. Red equal to band 122. NIR equal to band 167. If we all until this part, so now I have only two layers, one red layer, one NIR layer, which is coming from my TIFF file. And now I want to see the NDVI layer. Let's do a little muted here. Muted, I want to give the name NDVI. And my NDVI will be calculating from this NIR minus red, this red, which name I'm giving here. Divided by If we finish the coding, then this is our new layer. It has the red band, the inner ear band, and the NDVI layer. And we see all the numbers there, all the values there. So, okay. All right. So this is the NDVI, which gave us the best R square. Now we want to do a little plotting. That is why this is the last chunk. We will do a little ggplot here. So as we changed the layer as a star object, see, okay, as star object, we already know it will be a geom stars, and our data, from where our data will be coming from NDVI based. NDVI based. And we want our data to look, we want here to see the NDVI values according to the best combination. So it will be filled by NDVI. So fill equal NDVI. Okay. If we run this code, we will see this image here. So this plot is giving us the NDVI values according to the best combination. Here we want to do a little more thing. We want to bring the plots, or in this sense, maybe plot or the buffer from where we are collecting data. To bring that layer, we have to call the layer, which is, if we want to go there, the layer name was plot buffer. As we are working with stars, not buffer V, not plot buffer V. If we run until this, so we are calling, we want to see the plot with the NDVI values, and we want to see the plots here. We are running until this. We see all the plots are here. Because why we are doing this? Because if we want to see the variability of NDVI in the field, we can call the names that this plot number 1, or this plot is giving low NDVI, whereas this plot is giving high NDVI. That is why we want to do this, but still we don't have the names of the plots. To do that, we want to do another layer of ggplot, which is labeling the plot numbers. For that, our data is coming from our plot buffer. Now, how we are going to label our plots? So if we run only the plot buffer, we'll see that the plot buffer has 2 attributes. One is sample ID, which has all the plot number and the geometry. So right now we have only the geometry. We just saw the geometry, but we don't have any name or number on our plot. So we want to label according to sample ID. That is why we want to use AES. We have one function called label, and we want our label as sample ID. Make sure the sample ID spells correctly. if we run up to this chunk, up to this portion, we will have our NDVI plot with all the plot number. I want to change here one thing. The name of the bands, it should be NIR 167 and red 122. Okay. So here we see the variability of NDVI in the field. 714, 717, these plots has higher NDVI values. Does anyone have any question here? If not, then we just want to save the ggplot. To save this, we'll save this in output and give the name NDVI 167 and 122. You can name as you want.
Question.
Yeah, sure, Aman.
In this model, like empty spaces.
Empty spaces for soil pixels, we removed the soil, that is why.
Okay. So how are we gonna, so what about, like, for example, in plot, there is still some empty space. We're gonna do further.
Okay, so Aman has a valid question here that she asked why there are some empty spaces, and I'm not sure if you asked that maybe this plot went beyond my field, right? So today we changed one thing, that we made a buffer of 15 meter. That is why some of the plots went beyond field, like here. This is one thing. So I made buffer of 15 just to run this exercise, but in real life I will not do that big buffer. 15 meter is a very large area. I will not collect data 15 meter, or if it radius count, then 7.5 meter away from the points. No, I will not do that. And for real life analysis, my pixels are really small, 5 centimeter. So it will take the average of lot of pixels. But today we just did average of 3 pixels. So 1 pixel is 5 meter and I put a buffer of 15 meter. So more or less it averaged only 3 pixels. But in real life, real analysis, it will do the average of a lot of pixels. And then at that point, my buffer will be less. It will not go beyond field. But that question is really good, because if we do, or if we show this kind of analysis in here, in somewhere, people will ask question, and that will not give our real value. Good, thank you. All right, so this was the end of this exercise. I'm not sure if Dr. Bastos wants to give a break, because I have to say something like 10 minutes. To wrap up. Yeah.
So if you want to give it 5 minutes.
All right, so let's take a break of 5 minutes. After that, I will just wrap up the class, and want to mention some things about this lecture. You can take a break of 5 minutes. We will come back after 5 minutes. we'll come back after the break. I hope everyone could catch up the coding part, and I hope you understood a little bit. I don't expect to understand everything, but I want to give you a floor if you have any questions here after some time after finishing what I want to mention here. So feel free to ask question. If you have any question or any understanding what I didn't mention or failed explain properly. Okay, so today what we did in this exercise, we discussed in our lecture how head wall hyperspectral imagery workflow works. Then in the exercise, we extract reflectance value from a stacked raster, and we saw some of the layers from our stacked raster. We saw some of the layers, which I try to show first 16, but you can see all the layers. Then we calculated vegetation indices, just one vegetation indices, which is NDVI, with all the band combinations. And then we found the best vegetation indices combination. We found our best two band, which can explain our NDVI best according to R square. As we finish that, I want to explain the quizzes. I hope you all did well. So the first question was, what is the main difference in RGB, multispectral, and hyperspectral? I want to apologize because in some part I used HSI and in some part I used HIS, which is confusing. It should be HIS, which is Hyperspectral Imaging System. So what was the main differences? And the answers were B, C, and D. A was not the correct answer because A says RGB bands can separate from each other and plot. No, it can't. Hyperspectral, in one hyperspectral TIFF file, we can separate all the bands. And also in multispectral, we can separate the bands. But in RGB image, we can't separate the bands. We can't separate three different bands. One is red, blue, green. We can't. Just one image and we see three different colors. But in multispectral, three images, three different colors is the main difference. So this was confusing. What are the calibration? Because I talked about so many calibrations, but I mentioned here what the calibration we used in a UAV. So geographic calibration or geometric calibration, we do it in hyperspectral imaging. We don't do noise calibration. Yes, I mentioned that we want to remove the noise, but that is radiometric calibration. It is not noise calibration. Which is in D, radiometric calibration. We do radiometric calibration, not noise. And C, atmospheric calibration, we do when the data is coming from satellite, not from UAV. The answer is A and D. Okay. Third question was bandwidth. When we said that this sensor has higher spectral resolution, that means that band has very narrow bandwidth. Let's say 2 nanometer, it's a narrow bandwidth. 50 nanometer, that's not narrow, that's a very big bandwidth. So there I mentioned two sensor. One has 200 radiometric electromagnetic range, 200, and it has 10 bands. That means that 200 divided by 10. That means 20 nanometer is the bandwidth, but or spectral resolution is 20 nanometer. And the second sensor, it has range of 100 and it is divided into 5 bands. That means resolution is 20 nanometer. That means both the sensors has same spectral resolution. Number 4, the common use of hyperspectral in precision ag. Yes, it can estimate chlorophyll and nitrogen. It can differentiate crop and weed, but it can't give us the height of the plant. Yes, we use hyperspectral imaging to see the variability in crops. So, but that is not direct. In indirect, like I'm sorry, I don't want to go in that line. Height cannot be explained by hyperspectral imaging because it is flat. It doesn't give me terrain information. It doesn't give me Z dimension, right? Which is given by LiDAR, but not with hyperspectral imaging, and it can detect diseases. Number 5, from which sensor we cannot get a hyperspectral cube? Yes, satellite data gives us several bands, which means several bands means another dimension. That means it gives us cube, X, Y, and all the bands. That means cube. UAV mounted data, which was our data set for today's today's lecture. It gave us cube. Handheld hyperspectral images also give us several cubes, several layers, several bands, but reflectance sensor only gives us values, only gives us number. It doesn't give us image, doesn't give us cube. Okay. If anyone has any question here. All right. Next, I want to mention that I showed the way I am following for my data analysis data analysis, because image processing is fixed for every sensor. There are some rules, but not every sensor gives that process every step clearly. We have to go through different literature and everything to find that, but it is more or less fixed for sensor image processing, but analysis is different, because I am comfortable with a raster file. That's why I worked raster. I try to get the raster file of that hyperspectral image and analyze with this. But a lot of literature says that hyperspectral is easier to work with NV software. And in R, people use that HSDAR package, and with that package, the file name is different. For me, I am using with TIFF file, but when we use that file, that package, maybe the file name is header file or something. So we have header file. We have different files, but we don't use all the files. I use TIFF file, but other people can use header file to work with that package in R. Other people use NV software, but there are other software packages. I don't know everything, but I want to mention these things. Yesterday after last class, after finishing the class, Aman asked me what happened beyond that range, because I mentioned hyperspectral camera can capture between 250 to 15,000 nanometer. But in precision ag, we are interested only 400 to 2500. Yes, 2500 or 2.5 nanometer. Because in this region, we have visible range, near infrared range, and shortwave infrared range. But beyond that range, hyperspectral camera works. Hyperspectral camera used to capture small things like in medical or biological research. They use hyperspectral. I don't know much, but most of the hyperspectral are using in geology because it is really widely used to differentiate different rocks and minerals, because different minerals give the reflectance differently. They are very distinctable. So that are the other uses, and there could be other uses, I don't know, but yes, I want to mention that. And applications, I already mentioned some of the applications. I want some ideas from you today. Just give some ideas where we can apply hyperspectral images in precision ag according to your understanding. And before going to do that, I want to mention some challenges what I face. So I showed you the emails that hyperspectral images can differentiate plants and soil because their reflectance is very distinctable. But that is the main challenging thing. So soil gives more or less same level of reflectance in all the range, visible and near infrared range, but vegetation, it changes. In visible range, the vegetation gives lower reflectance, but in near infrared range, the reflectance is high. But it's not same. It's not straightforward all the time, because in here the soil is reflecting. The soil is white. I mean, we can see the soil, but in some cases soil is black. Soil has more water or less water. In that case, the reflectance varies. This is a sunny day, but sometimes we collect image where the exposure is lower, and reflectance from soil it is higher, and reflectance from soil from vegetation it is lower. So they cross with each other, which is really hard for us to differentiate. So these are some challenges, and I told you that they have a lot of data storage, and to just run one single line to call one single file, it takes too much time. Those are the challenges. And last thing, Polly asked me about the exposure. So that's the term I forgot. That is the exposure, because you can remember if you want to take a picture or image in a very low light, we change the exposure. We want more exposure so that the image will be higher. So before starting the hyperspectral sensor, we check the exposure. It should be around 3000. Yes, if there is too much cloud and the exposure is not high enough, the sensor will not start. And if it is very, very sunny day, there are lots of exposure, we want to lower the values. We tell the sensor, please don't go beyond 3000, because then it will be again problem. So that is the things I wanted to mention. And finally, I just want 2 or 3 applications you have in your mind for hyperspectral, because we are running out of time. We have 2 minutes before I hand over the class to Dr. Bastos. If anyone has any idea about applications of hyperspectral in precision ag.
Maybe we can
Aman can go first.
I'm going to Aman, but first Tifton, who has some idea.
Hyperspectral can be used to know the status of plant, the healthy and unhealthy plant.
Yes, thank you. Yeah, we can do that. And NDVI also does that with hyperspectral. We can do that. Thank you. Thanks, Polly. Aman, what were you saying?
Yeah, it can used for identify the weeds.
Yes, it can identify weeds. And here is one. Thank you. That is, Aman was saying that it can identify weights. Yes, because reflectance is different from plants and weeds. And there is one challenge in wheat research, because wheat and some weeds give more or less same reflectance. So there are challenges, but yes, this is one applications. All right, guys, thank you for bearing with me. I hope I could give you some knowledge about hyperspectral, and if you have more questions, or if anyone plans to work, please feel free to reach out, and thanks. Have a good semester. I'm handing over the class to Dr. Bastos. Bye.
Bye. Thank you.
Thank you.
Thank you.
All right. Well, first, I just want to thank Neva for teaching us a lot of resources related to hyperspectral. I guess as you all saw, it is a very powerful technology. It has a lot of benefits and also has some challenges, as Neva was sharing with you from her experience working with hyperspectral. So one thing that I just want to share with you about that specifically, when Eva was preparing the exercise and we were talking about it, the best way to go through that, so some of the initial files that Eva was using to prepare the exercise were really large. It was like 4 gigabytes, I think, Neva. So really large files, because on her sensor, she has a very small pixel size of 40 gigabytes. Okay, even larger than what I remembered. So 5 centimeter pixel size, and also across 272 bands, right? That's why they were so large. And we could have shared that data with you and worked with that data. The problem is that anytime you have data that large, every single thing you do, even the simplest function, is going to take a long time. And that was not the goal. The goal was not for us to run a summary on that type of object and wait for 30 minutes to see the results. That was not the goal, right? The goal of this class was for you all to learn really the differential that hyperspectral brings, which is number of bands, right? So I proposed to Neva that we downsampled or made the data coarser in spatial resolution, meaning to decrease the pixel size from 5 centimeters to 5 meters, just so it would become a lighter file that would still allow us to explore the bands. So that's what we did here. That's the reason why you're seeing you worked with such a coarse spatial resolution file, is because that was the only way we could work with a file that would not take a long time to do simple operations in R, and it would still give you the opportunity to explore the main difference of hyperspectral, which is the number of bands, right? So that's why we're working with this file, and Neva explained that, but I just wanted to stress that again. Another thing I wanted to mention here about hyperspectral is that, so a lot of times when we're using multispectral, so like when we did the exercise on the variable rate nitrogen using drone data, or maybe using satellite imagery to do the spatial temporal stability classes, all that is multispectral, right? And a question that I get a lot, and then if you're working with imagery, you may get that as well, is, so if you think of the nitrogen exercise, we were relating that response on the vegetation index to nitrogen. And then maybe somebody's going to tell you or going to ask you, well, how do you know it was nitrogen? Well, we know it was nitrogen because the study was a nitrogen study, and that was the limiting factor. Everything else we assumed was controlled, right? So we know that pH was at the right level, phosphorus, potassium were at the right levels. We were controlling for weeds, controlling for disease. Irrigation was not a problem. So the only other variable, or the major variables that was changing, was nitrogen. Also because we had a nitrogen reference on the field, which helps you to separate the effect of other stressors and nitrogen stress. However, really, with multispectral imagery, unless you have those checks in places, those references, you do not know why the crop is healthier or less healthy. There's no way that just by looking at so let's say if you get imagery from a grower that you're working with, and all that you can tell the grower is, well, we have parts of the field that are healthier and parts of the field that are less healthy. Now, the reason, just from the imagery, you're not going to know. You're going to have, what you can do is tell to the grower, maybe their consultant, hey, go to this area, pull a sample, pull soil, plant samples, and go to this other area, which is different in healthiness, and also pull plant and soil samples. Let's compare it, so then we can find the diagnosis of why they're different. Then after you get, lab results for plant material, for soil material, then perhaps you can come to a conclusion of the diagnosis of what is causing that difference in plant health. This is when we use multispectral data. With hyperspectral, there may be a better chance of you finding a very specific band, or maybe combinations of very specific bands that relate directly to a stress. And that is one of the powers of hyperspectral. So let's say Niva is studying aflatoxin, right? So aflatoxin, again, is a byproduct of a fungus that infects peanut pods when they're still in the soil, right? So first off, the sensor, regardless of what sensor we're talking about when it comes to optical sensors, the sensor is not even looking at the actual target, which is the peanut pods, because they are on the ground. So we're trying to use the plant as a proxy for what is going on with the plant above ground biomass and relate that to what is going on below ground. With multispectral, you could do that. You're probably going to be able to find some level of correlation. It's probably not going to be very high. With hyperspectral, maybe there is a very specific band on any of the regions that we have bands for, that very narrow band is highly correlated with something in the plant that is correlated with aflatoxin in the roots. So with hyperspectral, we have that higher chance of finding a very specific band that relates to the stress you are studying. With multispectral, that's very unlikely that you're going to find, you only have maybe 5 to 10 bands to begin with. It's very unlikely you're going to see one band or one combination of bands from multispectral that will explain a very specific stress. It will explain crop health overall, but a very specific stress diagnosis is very difficult to do with multispectral. Hyperspectral just gives you that stronger potential of, maybe if you calculate NDVI with this very specific red and this very specific infrared, that is the best combination to relate to aflatoxin stress, or maybe nitrogen stress, or maybe other type of stress. That's really one of the biggest powers of hyperspectral. And I just wanted to make that point here as well. All right. I guess any questions for me or Niva at this point? All right. I don't hear anything. So I think we're getting close to wrapping up for today. Again, I want to thank Niva for putting a lot of time and effort in preparing this great material. I learned a lot myself. I'm sure everyone was able to learn some new skills when it comes to hyperspectral. So I really appreciate Niva's effort and time in putting this together, especially because Niva's going through her preliminary exams. So that's another important thing going on in her that requires her time and attention. And so she was able to really put a great material together for us in class. Appreciate that. And then other than that, our next and last class meeting is going to be next Tuesday. That's our last in-person meeting. I do ask all of you to come. We're going to have a extra credit potential that is only going to be in class. So please, if you can, please make sure that you attend next Tuesday. And then we're not going to have any more new material, but I'm going to really just open up for that extra credit opportunity. And also, if anyone has any questions, or maybe if you want to talk about the final project, if you're going through issues, we can just take that time to go through final project related questions and work on that. All right, before we close here, anyone has any thoughts or questions?
Not about the lecture, but about the project.
Can you repeat that, Benedetta?
Not about the lecture of today, but about the final project, because I'm having the issue that I post on GitHub, and I don't know how to resolve it. Like, I try to run a different k-means and everything, but still, there is like one of the cluster that has all the variability of the yield, and the other that doesn't have.
I saw your comment. I did respond to that, asking for you if you could share the map of the clusters. I don't know if you had a chance to do that. Maybe you did, and I didn't see it.
Yes, I did that.
Okay. Yeah, I'm opening that right here just to check that. Yeah, that is yeah. I mean, I'm just looking at the clusters. It's very interesting that's what you're using, or sorry, that's what you're finding. To tell the truth, this is fresh data that I got this year, so I have not done the final project using the data you have this year myself. So I don't know exactly what types of challenges you're gonna find like this. Yeah, I'm just looking again at the proportions here, because really it seems like a lot of, like, you have all of your stability classes happening in cluster 2.
The maximum that I achieved it was having 50% and 50% on the unstable, but still one did have the high stable on the unstable. But still one had all the high stable or the low stable.
Could you share also on that GitHub issue, could you share a map of the spatial temporal stability classes as well, just for me to take a look and perhaps be able to comment on that? Yeah, well, I guess we're not gonna have time to fix that right now, Benedetta, but if you once you post that, I will get back to you on that issue. I do want to let everyone know I just opened the attendance for today on GitHub, so please go ahead and claim that before you leave. Also, something else I wanted to mention is that, again, you're all working on your final projects. You're all working with like growers data. I mean, we were working in class with growers data as well, but we're working with new growers data, which perhaps brings you new challenges, new things you're going to have to figure out how to deal with that you did not have to think on the data set that we worked in class. And that is also part of this exercise. Like, this is real world data, right? This is a grower, is data from their farm. It could be, a grower that you work with, or maybe if you open a company for consulting, this could be a data that would come down to you, right? So a lot of just the overall process of how you approach and the decisions you make, there's not necessarily like a correct answer, as long as what you're doing is intuitive. As long as you come to a conclusion that is intuitive, that makes sense, there's no wrong answer as long as it is intuitive. Just wanted to let you all know. So, if you make a decision of treating something one way or another way, or whatever it is, as long as you can back your decision up with data and explain to me what you did, I'm good. I'm good with that. Also, please make sure that you all use GitHub if you have issues, especially that many of you are working on the same data, and you're gonna run into similar problems. You're gonna run into similar issues as far as like, oh, well, this came up. I don't know exactly what to do. Maybe I can check with my colleagues and see how they're handling this. I'm completely fine with that. To me, that's not cheating. As long as you're not copying and pasting code from other people completely, you can share challenges, you can share difficulties, especially on GitHub, so others can also benefit from it. I'm okay with that. All right, so we are a little bit past time, so I just want to wrap things up here. Please, I saw that you posted on GitHub, Benedetta. I'll respond to you right now once we finish class. But if everyone make sure that you claim your attendance and then keep working on your final projects, as that is gonna, as you know, it takes some time. So if you have not started yet, I highly encourage you to start as soon as possible. And then I'll see you all on Tuesday, where we're going to talk again. I got about an extra credit assignment and a little bit more about the final project as well. Thanks, everyone. Thanks, Neva, again. Really appreciate it.
Thank you.